welcome back to our next episode of Architecture for Business Applications. This one is going to try to put together a lot of things which we have covered in the earlier episodes to try to address realistic looking case studies of constraints put on us, on our development and on our design teams by our clients. All of this is hypothetical. None of these actually refer to a specific real project, but we've seen enough projects by now to know what they look like, to know what kind of constraints hit real systems. So, the first one, the last 10 transactions challenge. Now, what is this last 10 transactions? I think I had mentioned it in an earlier episode, but this one will be a bit of a deep dive into it. Payment systems, payment processing systems collect payments from merchants, and a merchant will be talking to a customer, selling him some item, taking the credit card or UPI payment from the customer and pushing it into his system. So, he might use a physical card reading machine, or he might present a QR code to the customer for a UPI payment, whatever it is. Now, these electronic payments need to be cleared and need to hit the merchant's bank account, right? So, even if the money doesn't get deposited in the merchant's bank account till tomorrow morning, the merchant needs to know that the card that he has charged a few seconds ago has hit the payment processor. So, the payment processor is a third party service provider, very often a separate company, sometimes a bank itself, which is processing all the charges from a particular set of cards for a particular merchant. So, when the merchant swipes the card, the device talks to the payment processor server. The card swipe device talks to the payment processor server and registers the transaction there. Now, what does the untrusting, skeptical, unsure Indian merchant do? Within 5 seconds, he goes to the other screen of the charge processing device, the credit card device or his payment terminal, and checks to see the last 10 transactions within 5 seconds. And he wants to see that last transaction show up when he checks the last 10 transactions. So, every time he charges a card, he is looking into the last 10 transactions to see whether the charge he has just done is showing up or not. If the charge is not showing up, it means one of two things. The card is faulty, even though the device said the charge had been approved, or the payment processor is running flawed systems. His systems are not giving the right results. In both of these cases, the merchant will become distressed. So, this is a very real business requirement. What does a payment processor's software architect do to design systems such that transactions can be hitting the basic server a few thousand times a second, and still whenever the transaction hits, it is understood that there will be 50% of the cases, there will be an immediate follow-up call for the most recent transactions in the transaction table, and that has to be pulled out from the transaction table and shown to the merchant. So, the transaction, the charge that is being done hits the transaction table as an insert, immediately followed by, within a few 5 seconds or 10 seconds, immediately followed by a query to pull out the last 10 transactions of that particular merchant. So, this is a phenomenal amount of load on the transaction system when we are already talking about a few thousand transactions a second. So, the first thing to do is, we know the mantra, horizontal scaling. So, we need to distribute the web service load across a cluster of servers. We cannot talk about one server, okay. So, the servers will be able to, the application server code will be replicated, it will be able to handle the processing load, the CPU load will be handled. What about the database? to handle the database load and to reduce the load on the database, what the architect can do is he can cache the most recent transactions in RAM. So for a particular situation, we had done some calculations where we had talked about like 100,000 active merchants and 1,000, 2,000 transactions every second, and we had come to the conclusion that for this kind of data to be cached in RAM, we will need about 50 GB of RAM. Now, when we have tremendous latency requirements, tight latency demands, 50 GB of RAM today is not a very big issue with modern servers. So what we discovered is that it is very feasible to address these challenges using the fastest storage system known to technology, which is RAM. We discovered that it is doable even though the classic architecture which is used for such situations is an architecture where the query hits the database, and we don't know why it is done this way. So if you use a cluster of servers to handle just these last 10 transactions query, so you're basically building a microservice. If you use a microservice for this, then you can use a message bus to feed this microservice from the main transaction processing server. So one server, or you can say one microserver service, will handle the transactions where the data record is inserted in the transaction table. From there, a service bus, an enterprise service bus or a message bus, call it whatever you will replicate that transaction data to the query handling microservice. So we are talking about two services here, one of which at least is a microservice, the other also can be a microservice if you want, not really, but if you want. So we have a transaction processing service and a query handling microservice, and the message bus in between is the critical link. So the transaction server will first do the transaction. It will update the transaction database. By doing the transaction here, it means it will take the data, send it to the payment switches, the payment processing switches of the payment industry. The payment processing industry have their own dedicated switches which are used to connect credit card devices, ATMs, etc., etc. The switches will send the transaction data to MasterCard or Visa or RuPay, will get clearances from the issuing bank for the card, will report back to the transaction server saying charge is done, this transaction is successful. That is what it meant by transaction server will first do the transaction. Then it will update the transaction database. After the transaction database is updated, it will post a message through the message bus to the query server. So the query microservice will get this data and keep it in RAM. Each last 10 transactions microservice will hold only the cached data of the users who have queried it recently. So there is no need for us to to prime the cache with the data of all users. At any point in time, only a few merchants, 5-10% of the merchants are alive or are active. So we need to only hold the transaction data for those merchants in the cache. If a server in this cluster, in the microservice cluster, crashes, there is no harm done. That server can be rebooted or a new instance can be started, and the cache will build up over time. So when a new server starts in this cluster, it will pull data from the transaction database. But once it pulls data from that database, it will hold it in memory. It will not repeat that query again. So after the server starts up, it will rapidly get updates over its message bus. It will not do any queries to the transaction tables, and the database will never see the load of the queries. On the other hand, the microservice will literally be able to respond to the web services in a matter of microseconds, because there is no network traffic, there is no querying of a database. It is data being returned from the RAM directly. So the last 10 transaction challenge can be very effectively handled given modern hardware and large amounts of RAM simply by partitioning the roles and having a microservice which handles this query entirely from RAM. The next case study. This is very interesting. Of course, it is very interesting. Why would I give you the case study otherwise? Millions of users are querying an e-commerce system. or a hotel reservation system to see available rooms or available items which match certain search criteria. Now, the database of possible hotels or the database of possible items being sold may go into millions. The number of users who are querying this system also will go into millions. So at any point in time, in any second, you're probably expecting to see thousands of queries hitting your database. Now, in such a situation, if you are going to pass on these queries to the main transaction database, your system is doomed. And this is the classic architecture which a relatively thoughtless architect will give you. So what is most important here is to have a replica database which handles these queries without loading the main transaction database. So you have to separate the query database cluster from the transaction database. That is the first. And in this situation, one of the interesting things is users will accept slightly out of date information. Look at the last 10 transaction situation. The last 10 transaction case study required, one of its key requirements was that the most recent transaction must be included in the statement. So there has to be almost zero latency. Latency has to be in microseconds. That was its constraint there. Here, that's not the constraint. Here you just need to handle very large numbers of users, very large numbers of available items for sale, SKUs. It could be items being sold like physical items being sold by Amazon, or it could be hotel rooms which the traveler is searching for, or it could be railway tickets, airline tickets, whatever. So there are a very large numbers of items and there are very large numbers of queryers, but the status does not have to be extremely low latency, which means that the replication requirements are not that tight. So in that situation, one of the things you can do is to handle the very large volumes, you can shard the data across a cluster. So you can split the data across multiple servers and do a kind of map reduce. Pass on the query to all the servers, get a response from all of them, aggregate the response and send it to the user. The other approach is to have an array of read-only databases, but each database will have the entire data set. So if you have like 10 terabytes of data, then have 5, 10, 20 replicas, 5, 10, 20 databases, each database with 10 terabytes of data, having all the records, and basically the load of the query just gets distributed, just like a load balancer concept. It gets distributed across the databases. So the first step is to replicate the data from transaction database to query databases. The second step is to spread out the query database from one database to 10 databases or 20, whatever, so that the load can be distributed. Once that happens, you can have a very large number of users or customers querying your database. You can have horizontal scalability. And one of the chief problems of horizontal scalability is not applicable in this case, and that is the tight latency. So for the sharding approach, sharding can always be done at two levels. One is at the level of databases and other is at the level of applications. So a database level sharding is done using a database software which understands sharding and hides the details completely below its API. Examples of databases which can do sharding effectively are Vitess and CockroachDB. These really can scale up to terabytes are a small figure. We are talking about very large databases, and they can handle easily several thousand queries or tens of thousands of queries per second, and they can handle the distribution of the data set across their physical data stores completely transparently. PlanetScale today, in fact, is a well-known, I think it's a unicorn in Silicon Valley, offering you a sharded database, very highly scalable database as a SaaS service on AWS. So yes, we have databases which can do sharding. Or you can use databases which do not understand sharding and the application does the sharding, in which case the application code will have to have database connections kept open with each shard. So you have 10 shards, let us say, and the application code will have database connections open with each of the 10 shards and will pass on the relevant operation to the relevant shard. It can be done at the application level. So these are broadly the approaches which can be used to attack this requirement. I'm not saying it's very easy to do, but it is very feasible to come up with a design which can do this effortlessly, finally in operation. The volumes will be phenomenal, the reliability will be fairly good, and modern technology can be used without using any rocket science. So this is the second case study, and it can be addressed very well. But intelligent architects are required. An architect who understands quantified volumes, throughput, database transaction speeds, etc. Now let's look at the third one. This is, they look similar, but they are not. The third one is something which applies to trading exchanges. Imagine a stock exchange. Say there are 2,000 different companies whose shares are traded every day. There could be 20,000 listed companies, out of which 2,000 are actively traded every day. So this stock exchange has shares of 2,000 companies actively traded, and there are 100,000 investors or 1,000,000 investors who are buying and selling very rapidly. The scenario in stock trading has become much worse because of algorithmic trading, so the throughput requirements of orders have really shot up. So we are talking about tens of thousands of orders per second. So a stock exchange is forced to handle tens of thousands of orders hitting it every second. And these orders have to be matched. A buy order and a sell order have to be matched, and trades have to be, closed, and information has to be sent back to buyer and seller. So it's an extremely high intensity, continuous heavy load operation. Of course, it also has its own peakiness. As I was saying somewhere in one of the earlier episodes, some of these trading exchanges say that 50% of the day's volume comes in half an hour. So it's a highly peaky load also. So the peak loads must be far worse than the daily average. So what do? The first thing to notice about such trading or such transactions is that the buying and selling of, let us say, Tata Motors shares has nothing to do with the buying and selling of SBI shares or the buying and selling of, name it, some other shares. So why is this the case? This is because if there are 100 buyers trying to buy, let us say, Jindal Steel shares and 50 sellers trying to sell those shares, they are only dealing with that one share. They don't care whether 1,000,000 other buyers are buying or selling or not buying SBI shares or HDFC shares, right? Because the buyers and sellers of one item have to meet. So once you understand this, then you realize that it is not one stock exchange, it is not one trading market, it is actually 2,000 trading markets, because we said there were 2,000 companies whose shares are being traded. So it is 2,000 completely disjoint trading markets of 2,000 different items. There is no overlap between the transactions of one share and the transactions of another. So once this is understood, you can start sharding your system itself. Not just the database, but even your resources. You can split your so-called trading system into 100 or 1,000 trading systems. So horizontal scalability is immediately available. So this is the first recognition, this is the first insight which allows for horizontal scalability. And at the application level, you need to look at the buy order or the sell order and know, okay, the buy order for Tata Steel shares goes here and the buy orders for SBI shares goes there, because that's where the SBI shares are being maintained and this is where the Tata Steel shares are being tracked. So the application can split the transactions at the application level without any overhead. Now, when you do sharding, you will need to have replicas of the shards just for redundancy and fault tolerance. So that is part of the overheads. And when you want to do queries, when you want to, let us say, do an overall market picture query or any other query which cuts across all these shares or all these companies, then you need to have query servers. Now, query servers will be separate servers which will receive updates from all these trading and transaction servers, and they will be maintaining an aggregate database. So separate the query database from the transaction database cluster and serve the queries from the replicas of the transaction server. That's another option. You replicate the transaction servers and use those for queries. And the third option is you use logical replication to build an aggregate database. To give you one example, we don't know what the internal architecture is, but IRCTC is India's biggest online transaction processing system. They handle railway queries, railway train ticket sales. So each train is a completely isolated world. Let me explain even more literally. The seats of the Mumbai-Delhi Rajdhani of 20th May are one world. There is no connection between those and the seats of Mumbai-Delhi Rajdhani of 21st May or the seats of any other train of 21st May. So every day of every train is an isolated universe. So the potential for sharding is fantastic because there is no overlap. There are no cross connections or cross data linkages. So in such a situation, IRCTC is able to do a lot of scale up, a lot of horizontal scale out, and they are able to, they are aiming to do, as per one news report, they are aiming to do more than 200,000 bookings every minute. So these huge volumes may seem like scary and daunting initially, but they are not really. I mean, they can be handled with the right architecture and an insight into the data. You have to understand what connections exist and what decouplings are possible. That's where you get your opening. So now that we have sort of finished the series, I will just throw some summary thoughts at you from my slides, and there are quite a few summary thoughts, and hope to wrap up. Okay. The first parting thought. We have learnt a lot about service-oriented architecture and microservices and all sorts of other advanced things, but small and medium applications running in a single data center can happily run monolithic. You don't need to make them into a service-oriented architecture. Think about service-oriented architecture when you are exceeding a few hundred web service calls. I have deliberately kept the number vague because where to draw the line is of course very contextual. But where you have more than a few hundred web service calls and where you have very different, very divergent, very varied user profiles and usage profiles. For instance, there are human users and there are API users. And some of the largest volumes of transactions are coming from only, let us say, the API users and not the human users, and so on and so forth. So when you have a mixture of different types of usage patterns, different types of users, and you have a very large number of web service calls, then a service-oriented architecture may help you partition the overall application into more manageable pieces. Microservices are a very good idea. They can be added to both service-oriented architectures as well as monolithic architectures. Pick up the 1, 2 or 3 situations where you need extreme performance, and for each of these you dedicate an Alfa Romeo or a Lamborghini or whatever. What about a Bugatti Veyron? It may be a Bugatti Veyron. So they can be added to SOA. There is So which brings me to the, anyway, we'll talk about that. The next important idea is RAM and caching are both underutilized in a lot of architectures. When performance is at a premium, you need to see whether you will get a benefit by using, say, 20 gigabytes of extra RAM. Because RAM is not being used enough. A lot of read-only queries can be entirely handled from RAM. Caching is underutilized, but then caching is overutilized blindly. So on the one hand, intelligent caching is underutilized. On the other hand, blind caching is overutilized, and there are dangers there. When you overutilize caching, the keyword here is blindly. When you overutilize caching blindly, you are often unaware of the consequences. You are unaware of transaction boundaries, race conditions, or other performance bottlenecks also. So either you will get suboptimal caching or you will get good caching with other problems, unless you know exactly how the caching layer works. One more point we see is that there is insufficient understanding about non-SQL databases and non-ACID databases. I am putting them both broadly in a single very broad bucket. So a lot of software designers have got so locked into the idea of transaction boundaries and ACID databases that they just cannot comprehend things like distributed databases with eventual consistency. Now, eventual consistency is a very powerful concept to give you very high scalability. The horizontal scalability which every architect is glamour struck by is easily available if you are willing to accept distributed databases with eventual consistency. But we don't see sufficient understanding among the circle we deal with for these things. So to take that same thought a step forward, some architects over-design for absolute data correctness and absolute consistency. Very often, businesses survive very well with a small percentage of margin of error. But if I propose this to designers and architects, very often they go ballistic. Are you trying to tell me that we are going to play gambling with other people's money, etc., etc.? Extremely emotive responses come out, not from the brain, but more from some other parts of their consciousness. So they over-design for absolute consistency, and this reduces scalability. This point I think I have made before. If someone starts telling you about how fundamentally superior a pure microservices architecture is, just politely walk away. Don't try to get into a rational discussion with such people. One of the key points about architecture: there is no such thing as a best architecture in general. There is such a thing as a right architecture for a particular context. So just like there is no such thing as a best shirt size, you need to get the shirt of the size that is right for you. Right? So there is a lot of people who are not very clear about the fundamental underlying concepts of architecture often talk in terms of, oh, that architecture approach is old and outdated. Modern architectures are all like this. They talk that language. So they talk about best, they talk about good and bad. Architecture does not allow for such evaluation at all. There is only appropriateness. Now, final thought, and this is not actually one thought, but anyway, final slide, I promise. So there is this ancient Indian belief from ancient India that knowledge exists independent of the knower. Knowledge exists, full stop. The knower is one who finds the knowledge, who discovers or uncovers the knowledge. So this appeals to me, this makes sense. So whatever I have covered in these episodes is knowledge which I have uncovered, which is in the ecosystem. It is there, shared among all the practitioners who have designed systems, all the engineers who have suffered bad architecture, and all the developers who have struggled with various implementations. So this is not a set of videos where I share my knowledge. This is a set of videos where I have put together what I have discovered and presented them hopefully in some structured way. So if I have to use the analogy of author and librarian, what I have done is the job of a librarian. I have not authored a book. This is not my knowledge. And it's very important for you to take whatever works for you without getting deeply involved with the discussion of right and wrong. Okay, what is right for a particular context is not very right for another context, and there are very few subjects which are as contextual as architecture. So I'm hoping that in all these episodes there were many bits and pieces which you might have found useful. So pick those up, and those which don't sound useful to you should be just dropped. There is really nothing much to worry about verifying the correctness of many of these perspectives. But one point I suggest you don't let go of. Architecture is built on a foundation of non-functional requirements. So this fundamental connection, the NFR provides the foundation on which architecture is done. If architecture can be called a practice, then the practice of architecture is based on a foundation of understanding of NFRs and accompanying performance benchmarking. That's about it. So we've come to the end of the series. I hope you had fun. I definitely did. And this is like a summarization of more than 2 decades of work we have done in Remigis. And we keep doing interesting things and keep figuring out interesting insights about architecture all the time. Thank you.